Hello, this is the last subtopic of the chapter, and here we will learn about reacting masses and volumes. First, we're going to go over some key terms. The terms are not highlighted in yellow here, but I want everyone to be familiar to all these terms because you're going to see them very often. Reactants can either be limiting or in excess. Limiting reactants are the reactants that controls and determines the amount of products obtained. And excess reactants are those that are present in amounts that exceed those required to react with the limiting reagent. In a chemical reaction, we can't obtain an infinite amount of product. This is because we will always have a limited amount of reactants. Out of all the reactants, the most limited one will be called the limiting reactant, and it will determine the amount of product that will be formed. Usually, the limiting reactant will be the one that is most expensive or hard to find. Next, I'm going to go straight in explaining percentage yield. Percentage yield can be determined by the equation experimental yield over theoretical yield times 100. Because in experiments, due to both systematic and random errors, we will never be able to fully attain the theoretical amount that we have expected. The percentage yield takes this into account and shows what percentage of the theoretical yield was actually obtained. This is a question about limiting reactants, and it will help everyone have a better understanding of the concept. Let's take a look. 6 moles of Fe2O3 reacts with 9 moles of carbon in a blast furnace according to the reaction equation below. What is the limiting reactant and hence the theoretical yield of iron? So we need to find two things, the limiting reagent and theoretical yield. So first, we know that 6 moles of Fe2O3 reacted with 9 moles of carbon. Okay. The products are iron and carbon monoxide. First, we need to determine what the limiting reagent is. So, using mole ratios, I'm going to determine how much of iron Fe2O3 produces. Let's see. 6 moles of Fe2O3 will produce how much moles of iron? Fe2O3 and Fe is in a 1:2 ratio, right? 1 mole of Fe2O3 will produce 2 moles of Fe. So, moles of Fe2O3 will cancel and we will be left with 12 moles of iron. How about carbon? 9 moles of carbon right here. And carbon is in a 3:2 ratio with iron. So 3 moles of carbon will produce 2 moles of Fe. Moles of carbon will disappear, and this will be 6 moles of Fe. So Fe2O3 will produce 12 moles of iron, and 9 moles of carbon will produce 6 moles of iron. So which one is the limiting reactant? Carbon, because it produces the least amount of iron. So we can eliminate A and B from our answer. And it will give us a theoretical yield of 6 moles of iron. So the answer will be D. Next, I want everyone to stop the video and try this question on your own. This is a question also about limiting reactants. Okay, let's take a look. The equation for a reaction occurring in the synthesis of methanol is as follows. What is the maximum amount of methanol that can be formed from 2 moles of carbon dioxide, 2 moles, and 3 moles of hydrogen? The question says maximum amount of methanol. But actually, it's asking us to find the amount of product that the limiting reactant will produce. So we need to find the limiting reactant. 2 moles of carbon dioxide right here, and it's in a 1-to-1 ratio with methanol. So 1 mole of CO2, 1 mole of methanol. So moles of carbon dioxide will cancel out, and this will give us 2 moles of methanol. Okay, next. How about hydrogen? 3 moles of hydrogen, but it is in a 3-to-1 ratio with methanol. So 3 moles here and 1 mole. Moles of hydrogen will cancel out, and we will be left with 1 mole of CH3OH. So what is the limiting reactant? It's going to be hydrogen. And what is the maximum amount of methanol that it can form? 1 mole, right? So the answer is A. Now we're going to look at a new concept, ideal gases and real gases. What are ideal gases? Ideal gases are those that follow the kinetic theory of gases. Kinetic theory of gases is a model to explain and predict the behavior of gases at a microscopic level and is based on a number of assumptions. These assumptions are important, so you should all know them. Gas particles are made up of small particles, and their distances of separation is very large. The volume of the gas particles is negligible, so it's 0. Gas particles are in constant random motion. Gas particles undergo elastic collision, meaning that there is no loss in kinetic energy. Lastly, there is no intermolecular forces involved. And ideal gases, we usually say that gases at high temperature and low pressure behave similar to ideal gases. Then how about real gases? On the other hand, real gases are gases that do not follow the kinetic theory of gases, and it refers to gases at low temperature and high pressure. Now, ideal gases follow these 5 gas laws: Boyle's law, Charles' law, Gay-Lussac's law, the combined gas law, and the ideal gas law. We're going to look at each of them in detail. For a fixed mass of gas, Boyle's law states that at constant temperature, pressure, and volume follows an inversely proportional relationship. Under these conditions, if there is a change in either pressure or volume, it will follow this equation. P1V1 is equal to P2V2. Let's visualize gas particles moving around inside a piston. This is a piston, and there are gas particles moving inside it. If there is a decrease in volume of the piston by pushing the piston inwards, because the number of particles and the average kinetic energies of the particles is fixed, the pressure will increase, vice versa, because the particles, which are inside a smaller volume, will collide with the walls of the piston more often. This shows that the pressure and volume at these conditions show an inverse relationship. Next, Charles' law states that at constant pressure, volume and temperature follows a proportional relationship. And under these conditions, if there is a change in either volume or temperature, this can be explained by the following equation. Again, let's visualize a gas piston. There are gas particles moving around the piston. However, if we increase the temperature, the average kinetic energies or average velocities of the particles will increase. This will make them collide with the walls of the container more frequently, and thus it will eventually push the piston outwards, increasing the volume to retain back to its fixed pressure. Gay-Lussac's law states that at constant volume, pressure will follow a proportional relationship with temperature. And under these conditions, if there is a change in pressure or temperature, it will follow this equation. Again, if there is an increase in temperature, the average velocities of the particles will increase, making them collide with the walls of the container more often. However, in this case, since volume is fixed, the pressure will be increased. Finally, by combining these three laws, we can get the combined gas law. Let's try this question. A fixed mass of an ideal gas, so this is the condition, has a volume of 800 centimeter cube under certain conditions. The pressure in kPa and temperature in K Kelvin are both doubled. What is the volume of the gas after these changes with other conditions remaining the same? So we can actually solve this question by using the combined gas law. So P1 V1 over T1 is equal to P2 V2 over T2. This is the combined gas law. So here we can say that the pressure is doubled. So P2 is going to equal to 2P1. And the temperature is also doubled. So T2 is going to equal to 2T1. And here the volume is 800. So V1 is going to equal to 800. Now we're going to plug everything in. P1 here and 800 here over T1. P2 is equal to 2P1. V2 we don't know. And T2 is equal to 2T1. Now let's see. I can cancel out P1 and T1. Also, I can cancel out the 2's here. So we can see that V2 will be equal to 800. So there will be no change in volume. Lastly, the ideal gas law states that PV is equal to nRT, where P is pressure in Pascal, V is volume in meter cube, N is the number of moles, R, this is important, is the gas constant, and this is the value, it's a constant, 8.314 joules per Kelvin mole. And T is temperature in Kelvin. Kelvin is the same as Celsius plus 273. You can convert Celsius into Kelvin by using this equation. Let's try this question. This question is a very good question and it involves concept from previous videos. Okay, an organic compound A containing only the elements carbon, hydrogen, and oxygen was analyzed. A was found to contain 54.5% carbon and 9.1% hydrogen by mass, the remainder being oxygen. So the remainder, 36.4%, is going to be oxygen. Determine the empirical formula of the compound. We did this before in our previous videos. So we can change the percentage by mass into mass. 54.5 grams, 9.1 gram, 36.4 grams. By using the equation mass over molar mass, we can find the moles of each atom, and then by comparing them using mole ratios, we can actually find the empirical formula. So I'm going to divide each atom by its molar mass. So this is going to be 12 grams, so 4.542 mole. 1 here, and 1.1 mole. And the molar mass of oxygen is 16, so this is going to be 2.275 moles. Again, because it is difficult to compare these mole numbers, we're going to divide each mole number by the smallest of all the three different mole values. So the smallest is going to be the mole number of oxygen, 4. You can use your calculators here. because it's a paper 2 question. 2. So the mole ratios are 2 to 4 to 1. So we can see that our empirical formula will be C2H4O. Next, a 0.230 gram sample of A when vaporized had a volume of 0.0785 decimeter cube at 95 Celsius, which is the temperature, and 102 kPa, which is pressure. Determine the relative molecular mass, or the molar mass of A. We can approach this question by the ideal gas law. PV is equal to nRT. In this case, we're trying to find molar mass, and the mass has been given to us. So we are going to rearrange this equation a little bit to PV is equal to mass over molar mass times RT. Our objective of this problem is to find molar mass. So I'm going to rearrange this equation once more to molar mass is equal to mass times R times T over P times V. Okay, our mass is given in grams, so that's okay, but our volume is given in decimeter cube. But if you look at the previous slides, I said that the volume should be in meter cube. So I'm going to change this to meter cube. Because 1 decimeter cube is equal to 10 to the power of negative 3 meter cube, I can say that this value is going to be 0.0785 times 10 to the power of negative 3 meter cube. How about temperature? Because this is given in Celsius, I need to change it into Kelvin. So 95 Celsius, add 273, then this will give us 368 Kelvin. Lastly, our pressure is given in kilopascals, and we need to change it into pascals. That's easy. 102 times 10 to the power of 3 pascals. So if I plug all these numbers in, I am going to get 0.230 grams times 8.314 joules over K mole times 368 Kelvin. And P times V will be 0.0785 times 10 to the negative power of negative 3 times 102 times 10 to the power of 3, right? So 10 to the power of negative 3 and 10 to the power of 3 will cancel out. Here we can see that these two will cancel out if we multiply them, right? So I'm going to put in meter cube times. So if I plug this into the calculator, I'm going to get 87.9 grams per mole, which is about 88 grams per mole. So that is going to be our molecular mass of A. Now let's look at C. C. Determine the molecular formula of A using your answers from part A and B. So we know that the empirical formula is this, right? What is the molar mass of the empirical formula? 12 times 2 plus 1 times 4 plus 16, and this is going to be about 44 grams per mole. The molar mass of A is twice the amount, so I can see that if I double up the empirical formula, C4H8O2, I will be able to find the molecular formula of A. So that will be our answer for C. The Avogadro's law states that equal volumes of different gases at the same temperature and pressure contain the same number of moles. And this will enable the mole ratio of reactant gases to be determined from the volumes of the gases. This means that volumes of gases at the same temperature and pressure can be determined by the mole ratios. Next, molar volume. 1 mole of any gas will occupy the same volume at the same temperature and pressure. Again, at the same temperature and pressure, 1 mole of gas will occupy the same volume. Specifically, at this temperature, 273 Kelvin, and at this pressure, we usually call that standard temperature and pressure, STP, the molar volume is going to be 22.4 or 7 decimeter cube. Some textbooks say 22.4, some textbooks say 22.7. Just go by the one that your teacher teaches you. Let's look at this question. Consider the following reaction. If the reaction is made to go to completion, what volume of ammonia, this is a product, can be prepared from 25 decimeter cube of nitrogen and 60 decimeter cube of hydrogen. All volumes are measured at the same temperature and pressure. Okay, this is important. This question involves the Avogadro's law because at the end we see the phrase at the same temperature and pressure. So we can obtain the volumes using mole ratios. However, we first need to determine the limiting and excess reactants. This is because only the limiting reactant will help us find the amount of product formed. So 25 decimeter cube of nitrogen follows a 1:2 ratio with ammonia. So we'll cancel out, and we can see that nitrogen will produce 50 decimeter cube of ammonia. How about hydrogen? 60 decimeter cube of hydrogen follows a 3:2 ratio. So hydrogen will produce 40 decimeter cube of ammonia. What will be the limiting reactant? Obviously hydrogen, because it produces the least amount of ammonia. So the volume, 40 decimeter cube of ammonia, will be produced. Now we're going to learn a new concept. Do you know the relationship between the terms solute, solvent, and solution? First, a solution is a homogeneous mixture, meaning that all the substances are in the same phase, of a solute that has been dissolved in a solvent. An example would be sugar water or salt water. In this case, the solute will be sugar and the solvent will be water, and this will make up the solution. Next, molar concentration. The molar concentration of a solution is determined by the amount of solute and the volume of the solution. So the molar concentration can be derived by this equation, and the amount of solute should be given in moles, and the volume of solution should be given in decimeter cubed, which is same as liter. Next, to find concentrations of substances, we can use a technique called titration. Experimental method of titration. Titration is a technique to find the unknown concentration. It's to find the concentration of a solution by reacting it with a known amount of standard solution. And titrations are usually done in acid and base experiments. This will be further explained in topic 8. That's it for this video, and I will see you in topic 2.